First things first, homework number 40. We've done 40 homeworks. Page 607, chapter 10, section 1, numbers 1 through 13, odd, and yes, that's it. It's very short. These are very straightforward. I decided we're not going to do parametric equations, polar coordinates, and stuff like that. It's just ridiculously boring. And it's just like we would spend a long time doing it, and then you'd be like, that's how you do it. There you go. Whereas we could go the direction we're going to go and learn something actually quite, I think, much more interesting and way more useful. So we're going to start differential equations. It's chapter 10. One thing I didn't write up here for homework, you have an extra bit, which is read. It's on page 24. And when you start this chapter,
24.
yeah, page 20. Page 24. It's at the beginning of this chapter. It says, now is a good time to read or reread the discussion of mathematical modeling on page 24. And I looked and I said, actually, yeah, you really should read this. So read. It's just page 24. It's just mathematical models. And in case our numbering's different, I don't think it is, but it's chapter 1, section 2. It's just the beginning of that. It's like the first long paragraph, and when you get to the section linear models, that's when you stop. Stop it. You can't read that. Can't read that. When you get to it's just that first big paragraph, and then linear models is the next section. Stop. You don't need to read that. Just the intro to that. It's quite good to get. It's quite good. And so. Okay. Here's your homework back, by the way. There's that. Here's that. And let's just get right into this. So I'm gonna get rid of this. You guys got this down? I want room over here. So read on page 24. Good context for what's going on. What a mathematical model is, how it's developed, how it's improved upon, and stuff like that. And so, okay, I cannot find, I heard this quote before, and I've said it, I've written it up, or said it in here before, but it's been attributed to Einstein, but I've looked, and I can't find that it's actually Einstein who said it. But anyway, the quote is, nature speaks to us in mathematics, and her language is differential equations. And so, when you're formulating a model is a mathematical description of some phenomenon, some real world problem, right? Now, that could be theoretical, like a black hole, like we've never gone to a black hole and like done stuff with it. I guess now by this point we have measured them, right? We've seen stars flying around the very centers of galaxies and stuff like that. We've inferred, there's a black hole there. But before there was ever any experimental evidence for black holes, just it kind of pops out of Einstein's theory that there should be something called black holes. They should have such and such properties. So that comes from a model. His general theory of relativity is the model, and so that's like how models come about in theory. But we also have empirical models, right? Or rather, you can make a model from empirical data. Like you have, say, time, and you're measuring some kind of phenomenon, say temperature, right? And it looks something, you have a bunch of data points that look like this, right? And your question could be something like, we would like some function which gives you the output, say temperature, at some given time little t. This is what you want. And that would be your mathematical model of the thing, right? Now, often, a model will take the form of a differential equation. I'm going to define what that is right now. A differential equation. So that's an equation which contains some unknown function. Now this is how the book says it. I'm going to write it up here, but we're going to talk about this in a second. It contains some unknown function and some of its derivatives. The way I would say it is, it's an equation that has derivatives in it. Why? Well, because sometimes this makes you think like that the unknown function has to show up in the equation. And that's not necessarily true. And later on I'll show you an example of one where the function itself doesn't show up, but a bunch of its derivatives do. And so that's still, I guess, I don't know, I would say technically a differential equation. I mean, it's certainly a differential equation. I don't know why they're saying it contains some unknown function. I would say rather, it's an equation which, given some unknown function, it's an equation involving the derivatives of that function and possibly the function itself. I could see why they probably went with this definition. Now that I say it, it doesn't sound that great. But anyway, so that's it. So, for example, we've seen these before, right? We've seen something like, we've had y double prime plus 2y prime minus, say, 3y equals 0. We've had something like this before, remember? Yeah. And I said y of, and it could be of any variable, but let's just call it x. And I've said that y e to the some number x solves this equation. Take the derivatives and figure out what k has to be. Yeah. Right? We've done stuff like this before, so this should. So, but look at this. There's the unknown function right there. There's its first derivative. There's its second derivative, and there's an equation right there. Okay, so that is a differential equation. Okay, a lot of today is going to be just terminology and stuff like that, and your homework's going to be very simple, I think. Okay, so here's an example. Okay, so there's your definition. Basically, an equation with derivatives in it. Here's an example. Population growth. Okay. Now, as with any model, we have to make assumptions, right? And that's going to govern, and we usually make these assumptions to simplify things. Like if you've ever taken physics, you'll often have, you'll say, you'll have some system like a box on a spring, and you'll assume that there's no friction with the box and the ground. Because if there's friction, you've just made your life way more complicated. But if there's no friction, then you can model this pretty well. You could have some kind of description of where this box is going to be given how far you push it or whatever, right? And that's the model you're looking for, okay? So in order to come up with a model for population growth, we have to make assumptions. And one assumption that seems pretty reasonable is to assume that the population grows at a rate proportional to, so this is proportional, okay, proportional to the size of the population. Think about a petri dish with a bunch of bacteria in it, right? If there's one bacterium there, it divides at a certain rate, right? And Well, I mean, maybe it does, maybe it doesn't. But it's going to divide, and now you have 2 of them. Then it'll divide again, and you have, or they'll each divide, and now you have 4 of them, right? And the idea is how fast it's growing depends on how many bacteria you have in there, right? And we could say, like, when there's 8, now after whatever it is, let's say they split every 5 minutes, now the rate that it's growing is like, it goes from 8 to 16, right? That's much faster than going from 1, or that rate is a lot faster than going from 1 to 2 in the same time, right? So we get, and again, this is idealized here. We're just saying, in general, a population, maybe it's people, maybe it's wolves, maybe it's bacteria, okay? But they're growing at a rate, but then that rate should be proportional to the size of the population. Seems reasonable, okay? And this is under ideal conditions, we're going to say. Under ideal conditions. We'll come back to this in a minute. So an ideal condition would be your bacteria are in the petri dish. There's plenty of food there, right? There's no predators coming in, like, you know, like bacteriophages coming in and eating up the bacteria. There's not like cold air blowing on it. It's ideal. It's in a lab. It's like perfectly set to grow, right? Then okay. So let's assume all of this. Ideal conditions, etc. There's no, and the petri dish is big enough because obviously when it gets to a certain size, it can't keep going. We'll get there in a second. But right now, these are the assumptions we're going to make. Now, whenever we're doing a model, we want to identify at least 2 things. What the input is, and in this case, we're going to take time to be the input variable. Your book is going to call it the independent variable. I like to think of it as the input. And let's make the population itself, let's give it big capital P for the number that's in the population. This would be called the dependent variable because it depends on time. I call it the output. Okay? Now let's think about this. What we want to try to do is translate this assumption into a mathematical statement. So we're assuming that the population grows at a rate. So in other words, the rate of change of the population is proportional to the size of the population. So let's think of it. The rate of change. So that would be the change in population with respect to time. In other words, the derivative. That's the rate, the change in population with respect to time, is proportional to. Now that means that there's some constant times, right? That's what proportional means. Times the population itself. Right? It's proportional to the size of the population. So here we have this. This, my friends, is a differential equation. Right? You have, it happens to have the function in it, okay? But there's an equation, and it involves some unknown function. We don't know what function to use for the population, but it involves a derivative of it. Okay, now just as an aside, I could just have easily have written this as p prime of t equals k p of t. That would mean the exact same thing. If I had named p something else, I could have called it y. Y of t equals y prime of t equals ky t. Or I don't necessarily need to use the y's, or use the t's. I could say p prime equals kp, like that. Or I could have said y prime equals ky. And these are all exactly the same differential equation. Okay, just a bunch of different ways of writing it. And it will be useful for you if you're going to do stuff with differential equations to be able to go back and forth between these ways of doing it. Because in some cases, you'll see. We'll get there. It's just good to be able to switch back and forth. Okay? But right now, we'll just use Leibniz notation here, understanding that p itself is not a variable. P itself is a function. And it's a function. This tells you what the input variable is right here, because, well, there it is, right? You can't take the derivative of p with respect to time unless p depends on time, right? So the dependent variable depends on the independent variable, in other words, the output depends on the input. Okay, so here we go. If the population, let's start with the worst case example. If the population is 0, what does that tell you about the rate of change of the population?
Can't grow at all.
It can't grow. Now, does that make physical sense in the real world? If you have a petri dish with no bacteria in it, well, no bacteria are going to grow, right? Or if you have a population like a town in the middle of Nevada, a ghost town with no people in it, it's not going to change, is it? Right? So if p is 0, this says that the rate is 0. That actually makes good sense, right?
Yeah.
Okay. Now let's suppose that p is positive. So we have some people in the population. Let's also assume, just for now, that k is positive. Assume that k is positive. What does that tell us? Yeah, that tells us. So then what? Then dp dt is it positive or negative?
It's also positive.
It's also positive, because if both of those are positive, that times that is positive, so that means that's positive. What does that tell us about p? P is, if the derivative,
It's also positive. Oh,
well, we know p is positive, but I don't care about positive and negative. What is it doing with respect to time?
it's increasing.
It's increasing, right? This is where all that stuff that we talked about, the characteristics. What do properties of the derivative tell us about the function itself? We would say p is increasing. So if this model says that if p is positive, and k is a constant, and right now I'm assuming it's positive. I could have assumed it's negative, but then we'd be talking about, I don't know what necessarily, I guess some dying population, I guess. I mean, maybe you have a dying population, that's what you're trying to model. In which case, you'd say, well, then we want k to be negative.
Wouldn't it just be less than 1? Wait.
What now?
Well, it would be negative, or it would be less than 1?
If k were a negative number, and p were a positive number, then this would be a negative number. The slope of p would be negative, and he would be coming down.
You can't have a negative amount of people.
You can't have a negative amount of people.
Okay.
Now this differential equation doesn't know that we're talking about people or populations or anything. So when we go to solve it, we're going to have to stop, because we'll get answers that won't make sense, and we'll have to trim our model down a little bit. Right now, let's just think about this. So in this case, we're assuming, okay, we're talking about ideal conditions. It makes sense to say that k should be positive, because under ideal conditions, that's ideal for growth. So this should grow. So if you have people or bacteria or a positive population, then it should increase under ideal conditions. Okay? So this is the kind of thing that we're doing with differential equations when you're trying to model something. You're saying, okay, let's make some assumptions here. So we've made a bunch of assumptions, and it seems like a pretty good assumption. Okay? Here we go. Pay attention. I'll write this in a different color. The solution to a differential equation, from now on, diff EQ. That's how I'm going to, from now on, differential equation, I'm going to write diff EQ. The solution to a differential equation is a function. You're not looking for a number. right? This says you have some function. And when you take the derivative of it, it's equal to some constant times the original function. You're not going to solve this and find, oh, p equals 5. That's not true. I mean, I guess, p could be a function of t, and it could be 5. When you take the derivative of it, you get 0. That's not the same thing as unless the constant is 0, in which case you have the most boring differential equation and the most boring function in the world. Well, the second most boring function, I guess. The most boring would be 0 itself. And oftentimes, it turns out that does solve this differential equation, right? Like if I said p equals 0, okay, take the derivative of it, it's equal to 0. Does that solve this differential equation? Well, 0 equals k times 0. Yes, that is a solution. Is that one of the ones that we care about? No. Nothing interesting is happening. We call that the trivial solution. And we're not really interested in the trivial solution. There may be more than one trivial solution. I guess p equals any constant. Any constant is also a trivial solution because p prime is equal to 0. And so
k would have to be 0.
K in that case, yeah, and so it's not really a trivial solution because that would be just a trivial differential equation because that would just be 0. And so yeah, okay, whatever. But the solution to so the whole point of the differential equation is to try to find a function, which is your model, right? Like I said, like I was showing at the beginning, you have a bunch of data, and you're like, I would like to know, here's my temperature, here's my time. I would like to know, given any time, what is my temperature? I want a function which, when I plug in little t, I do something to it, and out pops a big T, the temperature, right?
Yeah.
And the idea is, okay, maybe if we could, because we live in a universe that has time woven into it, and things change as time goes on. So oftentimes we're talking about the rate of something, and when we collect data, we have data about the rate of stuff, in which case you end up with something like this, just like what we did here, and that's like, well, now what do we do? I would like to find a solution to this differential equation. I would like the function, the model, that's going to work here. Now, in a couple of sections, we're going to be given something like this. You'll be able to go, I know exactly what to do to solve this. But right now we don't. So let's just use our brains. You took the derivative of a function and you got the function back. What does that sound like to you? Is there a function you know of that when you take its derivative it stays the same? E to the something, okay? But e to the x or e to the t. So I'm thinking here, this function should be e to the t, but then it looks like when I take the derivative of it, a k pops out.
Yeah.
E to the kt should do, let's just see what happens. This looks like a solution to this differential equation. Let's check it and see if it is a solution. So, take the derivative of p, and what do we get? K e to the kt. Now let's see if it solves this differential equation. Again, like I said, it's a lot, sometimes you want to be able to switch back and forth between these guys. So this is the same thing as dp dt. And so let's just plug that in. dp dt equals k e to the kt. Is that the same thing as k times, and we just said p itself was e to the kt. Does that work?
Yeah.
It does work. So p of t equals e to the kt is a solution to this differential equation. Is it the only one?
Probably not.
Probably not, because watch what would have happened if I did this. Let's use 3. Now let's take the derivative of this guy. P prime of t equals what?
3k.
3k e to the kt, which is dp dt. Now let's see if he solves this differential equation. We have 3k e to the kt. Is that equal to, we're wondering, k times p, which is 3 e to the kt. Is that the same thing?
Yes.
It is the same thing. So this also solves the differential
So it's like a
equation.
constant times.
So, yeah, and now we're going to say, wait a second. The 3 just kind of came along for the ride. If that had been any constant, any real number whatsoever, let's just call it c, we would have had this, and we would have had this right here, and this right here, and this right here, and indeed, that would have solved the differential equation. And so what we end up with then is we could say this is the general.
We've seen this before, right?
Oh yeah.
It was like NC is like the starting population.
There you go. There you go. And yeah, because think about time. What happens when time is equal to 0? P of 0 is what?
C.
It's just plain old c. And so if you think about this thing looks something like this, and it goes through right here. And so your population at time 0 is c. And we'll get into this in just a second. We're not quite ready to get there yet. But let me finish talking about it. So this is the general solution. And with a differential equation, so this is the general solution to this differential equation right here. And this general solution is not one thing. It's actually, we call a family of functions, or a family of solutions. Because c, let's just check this, c, I claim, can be any real number, and this will work. Even 0, right? Because we already saw that. If it is 0, you just have p is 0, and p prime is 0. You plug that into here. It works. It's trivial, but it does work. Now, if c is any other number, let's just see. If c is 1, then you have e to the kt, and we've assumed that k is positive, right? We're assuming now that k is positive. In which case, okay, if c is 1, he goes through here at 1, and he comes up like that. And so that's one solution. Another one would be that, let's say, c is 2. And you'd have this guy right here. c is equal to 2. That would be 1. Now maybe c is equal to negative 1. Does that work? Can I plug in a negative 1 here, and does it still solve the differential equation?
Yes.
I can. So it goes through at negative 1, he comes down like this. This is when c is equal to, say, negative 1. If c is equal to negative 1/10, I guess he would go through right here. He would hug a little bit more. C is equal to negative 1/10. And so what we end up with is, we can say that the general solution is really a family of functions that all look like this. And you could imagine if you let c go through all the real numbers, you're going to fill up this entire space with these family of curves that look like this. Okay? Okay, now, so that's called a family. As we let c vary through all the different real values, you get what's called a family of solutions.
It's a big family.
It is a big family. It's an infinitely large family. Uncountably large, actually. Probably Catholic. So, we're Orthodox. We're just as bad. Or good. Really good. Big families are awesome. Okay, so... Okay, now here we go. So, we made a bunch of assumptions. We came up with a differential equation, and then we just went into analysis land and said, okay, just work on this, blah, 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 blah. There's my family of solutions. Now let's step back and think about, do any of these make sense?
No.
can your population ever be -1?
No, that's not.
I mean, maybe you owe somebody works somewhere, so they have to go to a different. No, that doesn't make any sense. So now at the end, we're going to come back and say, wait a second, hold on. We want physically meaningful solutions. So we're going to say C's got to be a positive number. Can't be 0, otherwise, I mean, you got the trivial solution. We don't care about that. So in this context, to make this make sense, we're going to say, yeah, all real numbers will work here, but only the ones that are bigger than 0 are actually meaningful.
And
so for your petri dish or whatever,
doesn't it have to be a whole number as well?
well, yeah, right. I guess so, right? You could say, how could you have half of a person? But maybe you're talking about a petri dish, and you have millions of these things, and so you don't want to have C equal to 1,000,000. You could just say C. You could count by millions, right? I think we actually did that in algebra 2. It's like, let's let P be the number in millions of bacteria.
Yeah.
So then C equals 1 means 1,000,000, and
But you can have.
but no, you're absolutely right. If you're just saying that P is the number of people, then yes, of course, you can't have half a person. So, yeah. So anyway, okay. So, okay. So physically meaningful solutions, blah, 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 blah. Now, this model does not take the environment into account. Okay? So, let's refine our model here. Well, this is good for like petri dishes in a lab that aren't too full, because let's think about something that happens when a petri dish gets too full. At some point, you started off with 1 bacterium, but now enough time has gone by that they have completely filled up the petri dish.
So now you need 2 petri dishes just for the next 5.
Yeah, like they're running out of food, they're running out of room. This environment has what we call a carrying capacity. Okay, and do we want to do that now? Do we want to do this? Yeah, so the carrying capacity is some value of the population. We call it K, big capital K. And the book used little k and big K for what we're about to do. And I'm like, let's use a different name. But no, because that's where every book I've ever seen uses K, little k here, and big K for the carrying capacity. So we'll stick with it. But the carrying capacity is some number K. So that's the number in the population, the number of the population.
Where?
Yeah, well, here's the thing. Okay, so we'll get there. We'll get here. We'll get there. Just give me a second, okay? So let's refine this model, okay? And what we're going to do is say, all right, same assumption here. And in fact, we're still going to use T as time as our input. And P is the number in the population, which is my output. But now, we're going to make an observation. We're going to look at some actual stuff. We're going to look at our petri dish, or we're going to look at our wolves out in the wild, or we're going to look at the people in a town, and we're going to say, you know what? Populations start off growing exponentially. When they're small. Maybe we did this in the lab. We were just counting. We started off with 1 bacterium and we were counting time in bacteria. And we noticed that after 2 seconds, we had 2 bacteria. And then after 2 more seconds, we had 4 bacteria. And after 2 more seconds went by, we had 8 bacteria. And we say, this is growing exponentially when it's small. But we noticed that once the dish got really, really full, they're not expanding at the same rate.
Because they can't.
They can't. They're running out of room, right? Or maybe these aren't petri dishes. Maybe these are wolves out in some wildlife refuge that's fenced off or something. I don't know. We notice, okay, so they started off growing exponentially when they're small, but the rate leveled off. But the rate levels off as the population approaches some value, some maximum value we call K, which is the carrying capacity. Okay? Now, maybe that K value has something to do with predators, right? So like if we're talking about population of deer, as they get bigger now, the wolves notice them, and so they start to come in and get them. Maybe that those deer start eating off all the grass, and now there's no grass for them to eat. Maybe it's not an actual wall, but it's more like, well, now that they've eaten all the grass, there's not enough grass for all the deer, right? Something like that, etc. Right? There's, for whatever reason, be it the wall of a petri dish, or a fence around the lambs, or the wolves eating the sheep, whatever it is, there's some value. This is just what we notice, that the value seems to slow down as it approaches some K, the carrying capacity. Okay, so let's make a model which deals with both of these trends. The first one is, it starts off growing exponentially when it's small. So in other words, dp dt is proportional to the population when p is small. But then we notice also that if it gets above the carrying capacity, it shrinks back down to the carrying capacity. Right? So like, right, like you start to get, now you have around K of these bacteria in here, and every now and then you still get some splitting, but there's not enough food there, so a few more of them die off. And then there's some more splitting here, but then these guys start to die off, so maybe it goes above and below. What we notice is that when the rate gets above a certain carrying capacity, the rate becomes negative.
Okay.
Does that make sense? So in other words, what I'm saying is that dp dt becomes negative. The population decreases when P gets bigger than K. When you're past your carrying capacity, we notice that the population then decreases to go back towards the carrying capacity. Okay? Does that make sense? And this all just comes from observation. This is what we looked at in the lab, right? And we had our data, which showed like, oh yeah, this is, as time went on, it went up and it went up, and then it slowed down, and every now and then it gets above this value K, but then it decreases. And we notice that, and so we're saying, okay, all right, it's coming back. If he goes up, then the rate comes down and he goes back down to K or something like that. Or maybe we start off with a ton of these guys. We put 1 billion bacteria into here, and we notice that they're dying until they get down to the carrying capacity of the petri dish, or whatever. The point is, we just observed the real world, and this is what we've inferred from it. Now we want to try to build a model which sums this up. You will not be asked to do this. But what we could do is say, well, let's construct a differential equation which grasps this thing, or which does this. And so what we can do is this. dp dt. So the rate of change of this population, it's still proportional to this, but now we're going to add in another term here. In fact, we're not going to add in, we're going to multiply in another term and see what this does. 1 minus big P over the carrying capacity. Now, when P is small, this thing's like 1, and, oh, I meant to make this approximate here. So when P is small, this thing is approximately like Kp, right?
Yeah.
But what happens when P is bigger than K? Now,
it's negative.
1 minus this value, you get a negative. And so a negative times, we already said these guys are positive, makes a negative. So dp dt should then decrease because it's negative, so he should come back down whenever P gets up to the carrying capacity. What if P is equal to the carrying capacity?
Then there's no population.
Yeah.
Well, hold up. If P is equal to the carrying capacity, we have 1
minus 1.
minus K over K, which is 1 minus 1, which is 0, which then says like, oh, this guy doesn't change. He wants to stay there. He's stable, in a
So it
sense.
flattens out.
So we could say then that P equals K. We would call this an equilibrium solution. Because when P equals K, if you started off with K, what the model says, and of course this isn't the real world, but our model would say that if you started off with your population is equal to K, then your rate of growth would be 0, and so he would just be stable. He would be what we call an equilibrium solution. Another one would be 0. Because if P is 0, this is 0.
Yeah.
And so he's also in equilibrium. It's just a really boring equilibrium.
So that means like
That's another equilibrium solution right there. Let's figure out what we could figure out from this. Now, next time when we do 10.2, we're going to go into detail about what I'm about to do. So right now we're almost done with population growth, so I'm going to get rid of all of this. And I'm just going to put this differential equation up here. We have that the change in population with respect to time is proportional to the population times some weird thing which brings us back down to K if we get above K.
yeah.
Okay, let's get rid of this here. Now, when we do, what I'm about to write right here, we are going to go into great detail with next time in 10.2. So I'm just going to do some stuff and you're going to go, whoa, 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 hold up. No, we're going to go in detail in 10.2. And so what I'm going to get here is a qualitative solution here. Now, one thing to notice here, imagine that this right here were y, and that the p's were x's. So inputs and outputs. Could you graph that thing? What is this thing? What type of object is this?
It's
Kx minus kx squared over big K.
it's just a parabola.
It's just a parabola. And where are its zeros? If the input value were this and the output value were this, where are the zeros of this parabola?
1 over 0 k. No.
Wait a second. What value of x makes that part 0?
0.
0.
Yeah, so 0 and negative 1 over k. Wait. Oh, 1 over
1 minus what number over k equals 0?
K.
K itself, yeah. If you plug in a k for here, then you get a 0. And so this is a parabola. Is it an upward or downward parabola? Is it upward? It's downward because we have this minus right here with the squared term, right? And so we should do something like this. Now, okay, but it's not that. it's not an x and a y, it's actually a p and a k, or a p as the input, and the output is dp dt. In other words, it's the slope of p, yeah?
Yeah.
Okay, watch what I'm going to do. This is actually so useful because guess what? Most differential equations you can't solve exactly. We can solve this one exactly, and we will learn how to solve this one exactly in 10.3. But most of them you can't do that, and so what you do is something like what I'm about to do, which we'll go into when we do 10.2. We could say, hold up, okay, so I want my function p. What should that function look like? Well, it looks like the slope of the function depends only on what the value of p is.
Yeah.
So when p is 0, we already said if p is 0, he's not changing. So if the output here is 0, then it's going to just go straight like this. The slope is always 0 there. Yeah?
Yeah.
Ditto, if the value of p is k, then the slope there is also always 0, no matter what time you're at. Do you see time anywhere in here? I mean, it's per time, but there's no t value in there. So it only depends on what the output value is, p. So it says that the slope is 0 here. Now watch what the slope does when p is a little bit bigger. Oh, and where would this be? If this is just a regular old parabola, where's the vertex of that guy?
1/2.
Yeah, k over 2. There you go. Okay.
And
So,
that's also 0. Wait,
what now?
the slope there is also.
Well, we don't care about the slope. The slope there is whatever this output is. It's positive, because this is I'm graphing the slope of p
right
here.
right.
Right? Yeah. Yeah. This is what's so tricky, and this is why we're going to have a whole section devoted to this. But right now, I'm just down and dirty, just showing you what we're going to do to get an idea of what p could look like. Okay? So, when p is a little bit bigger, then the slope is a little bit positive. So it looks something like this. It's a little bit positive. When he's a little bit bigger than that, he's a little bit more positive. Until finally we get up to k over 2, where the slope is as positive as he's going to get. And so I'm going to draw that like this. More positive than anything below him, right?
Yeah.
Okay. Now we're between k over 2 and k. The slope is a little bit smaller, and so he comes back, oops, he comes back down a little bit, like that. And then finally, as we get closer and closer and closer to k, he's almost flat. Oops, that doesn't look right. Almost flat, but not quite flat. Something like that. Now, what happens when the value of the population is bigger than k? The slope is negative now. And so he's negative like this. Slope would be negative whenever you're at that value. You go further beyond and you get even more negative. Does this make sense what I'm drawing here?
Yeah.
We're going to go in depth on this next time. And so, if your population started off with this many bugs, then he would start off with a slope like this, and he would come up, his slope would get bigger, but then he would gradually decrease and decrease until he approaches this value. If you started off right here, your slope would be, well, kind of getting smaller and smaller the whole time like that. If you started off with a big population, you would decrease fast and then come down and slow down and again approach here. So this gives us, so this would be how we could generate a family of solutions depending on your initial condition, or really any condition in there, we'll get there, But this is what we expect when we finally go to solve this thing and we get my P of t is something. We're going to get some family of functions that do this depending on where you are. Does that make sense?
Yeah.
And like we'll get into how I drew all this and all of that. We'll do that in depth. And then we'll actually get an analytical solution in 10.3. We'll actually solve this thing exactly and find like, yep, it's this thing. It's one of those things. That's the form that it has. And now let's just stop and see if this makes sense. If you started at carrying capacity, our differential equation says that you would just be constant. Is that what we see here?
Yeah.
If you started above your carrying capacity, this part would be negative, and so your slope should be negative. Is that what we see?
Yes.
And he kind of dies off and approaches carrying capacity. If you start off small, if your population starts off small, it looks exponential, doesn't it? Comes up like an exponential.
Yeah.
That's what we said. If he's bigger, it's not really exponential, but he slowly approaches, like we said, the rate decreases as it approaches carrying capacity. So something like that. Yeah, that's pretty cool. Well, we'll get into how we do all of that. And we'll actually solve it analytically, get an exact solution in 10.3. Okay, moving on. A couple more things to talk about. Remember Hooke's law? Yeah, as long as there's no follow-up questions, yes, I remember it. Hooke's law said that with a spring, you have a spring, right? And it has some equilibrium thing. It says that by displacing it from equilibrium by a distance of x, it said that the force is proportional to that change right there. Now here's another thing. If I pull the spring this way, which direction is the force pulling it?
To the left.
To the left. If I displace it this way so that x is a negative number, which direction is the force?
To the
Right.
So it's the opposite of whatever the sign of this is. So the force is in the opposite direction. So you usually see it like this. That the force is equal to negative k. Why couldn't k be negative? Well, it could be, but the calculations work out easily if you just think of k as a positive number. Sorry. So this is the way that it is. This is how we usually write Hooke's law. But the force, Newton says that force is equal to what times what?
Mass times acceleration.
Acceleration, which is a function of time. But if x is my position, then acceleration is the second derivative of that.
Yeah.
Or I could write that as d squared x dt squared. That means the same thing, right? The second derivative, this is just a fancy way of writing the second derivative. And so the force is equal to mass times acceleration, mass d squared x dt squared gives us mass d squared x dt squared equals negative kx. And we have a differential equation.
Okay.
Because we have an equation that involves an unknown function, we don't know what the function is, and it's one of its derivatives, one or more of its derivatives. Right? The unknown function is x, and it's like, okay, we need an x of t. Now, can you guys think of a function where when you take the second derivative of it, you get negative the original function?
Cosine.
Yeah.
Cosine or sine, right? But they both have that property. So maybe this has something to do with a sine of something or a cosine of something. I don't know if we'll actually get to solve this one because this is, as you can see, a second order differential equation, as we'll talk about in just a second. But yeah, something tells me that the solution to this thing should involve sines and cosines. And if you take a spring, if you take a weight on a spring and you push it and let it go, what does it do? Does it just come back? Or does it bounce back and forth?
Yeah.
Yeah, so maybe it does have something to do with sines and cosines. Interesting. We're not going to get into this, but it's just something to note. So that's a differential equation. And so that brings us to the order of a differential equation. Order of a differential equation is the order of the highest derivative in the equation.
Yeah.
So first order, example of first order was our first one we worked on, dp dt equals kp. That's our first order. Another one was dp dt equals kp 1 minus p over big K. That's also first order because the highest order that showed up was the first derivative. Second order, here's an example, is this guy. D squared x dt squared equals negative k over mx. Or like we saw a second ago, y double prime plus 2y prime minus 3y is equal to 0. It's an equation. It has an unknown function. It has derivatives. The highest order is a second derivative, so it's a second order differential equation. Okay? Just definitions. A lot of this today is just definitions. All right. The independent variable, the input, does not need to be time. It could be anything. For instance, this is a differential equation, and it's implicitly telling us, because I didn't write dy dt, so it's like, well, you took the derivative with respect to what? Well, I see a y, it must have been x,
yeah.
Right? So it's kind of implicitly defined, unless they say specifically, no, that's a third variable. You're going to hate your life in a second. Like, now you have 3 variables to deal with. No. Like, if it's not otherwise stated, clearly it's x. And x does not have to be time just in disguise. You could have spatial derivatives. In fact, this is why, one of the reasons, so this is something called the wave equation. The second derivative of a function with respect to x is equal to some constant times the second derivative of that function now with respect to t. So in other words, you have some function u, and it has two input variables, x and t. And a function which behaves this way turns out to be a wave. That's why this thing is called the wave equation. Sometimes you'll see the c on the other side. Doesn't matter, it's a constant. Divide by it.
Yeah.
Right? So, but anyway, you'll notice, and this is why I said I don't like the way that the book says, this is a differential equation. It's a very famous one, very fundamental one. Like, and it shows up everywhere. And do you see anything but derivatives in there? It's just derivatives.
Yeah.
There's no u there. There's no plain old function. Like here, you're like, there's the derivative, but there's the original function. Well, this one doesn't have the original function in it, and it is a differential equation. So, I just had to go off on a tangent there. I'm sorry. But anyway. So, it's understood in this that the solution that we're looking for is y, and it's some function of x. That's what we're looking for. Okay?
Yeah.
So again, a solution to a differential equation to a diff EQ is a function which satisfies the equation. That is, if this function is a solution to this differential equation, then when I take the derivative of it and then I multiply it by x and multiply it by then this is equal, right? That's what we mean by satisfies the equation, okay? Okay, example. Show that y equals, what do I have, 3 e to the 1/2 x squared is a solution
Okay.
to that one. Simple. Let's just take the derivative.
Yeah.
Right. We've done these before, right? Like you've had homework before where it's like show that this is a solution to this differential equation. Okay, so 3 stays put. Derivative of e to the stuff is e to the stuff. Then we multiply by the derivative of the inside stuff. So we have 1/2 times 2x, which just works out to be 3 e to the 1/2 x squared times x, which is, let's write it as 3x e to the 1/2 x squared. Now, plug that into here, we get 3x e to the 1/2 x squared. Is that equal to, we want to find out, x times the original function, which was 3 e to the 1/2 x squared. Are those equal? So then, therefore, it is a solution to the differential equation. Is it the only one?
No. Any
C.
I'm willing to bet that we could replace this with any number c, and now we have a family of solutions.
Yeah.
And yeah, you could check for yourself. Any c, any real number c is going to work. Actually, any complex number c would probably work, but we're not going to get there.
Because it would just come wrong. That's probably-
What now?
Because it would just also come
It
along.
would just be c. It would just come along for the ride. Exactly. Now, remember, this is the general solution. And when we write that, there's actually a family of functions, right? The general solution is a family of functions. And maybe we restrict it depending on the situation, right? Or maybe it just won't work. Maybe when you plug in certain values of c, you get division by 0. Like, for instance, if you have, like, if it worked out to be that your thing was something like this, x e to the x over c, I don't know. Why would you do that, right? I don't know. Maybe your differential equation worked out like this. Well, then obviously you can't let c equal 1. So that would just rule itself out. Or maybe, like earlier, we said, well, negative values of c don't make sense in this scenario, right?
Yeah.
Okay, so now think about this. Here we go. We had something involving derivatives. We somehow undid the... I didn't say how we got from here to here, by the way. You will know in section 10.3 how I got from here to here. You will do that, and it's not as bad as you think it is. But let's just think about this. We had something involving a derivative. We somehow undid the derivative and ended up with infinitely many solutions. Does this sound familiar?
Like taking an integral.
We had something involving a derivative. We somehow undid the derivative, and we ended up with something involving infinitely many solutions. Something to notice, okay? Now, in practice, we're often more concerned with a particular solution, right? Like you end up with something like this, and it's like, yeah, but which one do we care about? Well, in our scenario, you know, like for instance, like with the population, you had, like, forget about the squared thing, but you had some constant blah, 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 but what was your initial population? And then we would need to find whatever C is.
Yeah.
Okay. Okay, well, let's just take a break here. Let's do this. Time, velocity. You guys took a car trip. Victor was monitoring only the speed of the car. And here he found this. He found it was always 60 miles per hour. And you guys drove for, let's say, 2 hours, whatever. That's not going to matter in just a second. Now, Noah already has a function which describes exactly where you were at whatever time, right? Victor, he's trying to come up with a function here. The original function. This is our goal here. We have some unknown function, f of t. And Victor says, well, I have a v of t. I have my velocity as a function of time. And I know that if I integrate it, then I'll get my original function that I care about. So he does that. He says, okay, I'm going to integrate, it's a constant value, 60 dt. And what's the antiderivative of 60 dt? 60t plus some unknown constant, right?
Which is, yeah, where you started.
Wherever we started. Now Noah, so this is what Victor has right here. Noah, on the other hand, he had the entire record of everything. He knew that we started at mile marker 100. He knew that we ended at time equals 2 at mile marker 220. And his data was nice and sufficiently in a row here for him to conclude, yeah, it was linear. We were going the same speed the whole time. So he went and found the rise over the run, right? He said it's a line, so it has this form. He saw that it went through at 100, so he said, well, that's the same thing as this, it's 100. And my slope was my rise over my run, which he calculated to be 60. And so he ended up with this right here. Victor has a family of solutions. But there's only one solution that's going to help, right? So to get the particular solution that he's looking for, what does he need?
Where you start. Okay.
That's
Like, just has to find C.
The easiest thing would be if we knew the initial condition.
Oh yeah, I guess you could
right?
know even one then.
You could do any of them, right? And I really want to drive this point home. All you need, because this is true, you're only missing one value here for C. All he needs is any one point along here. Let's just say that all he knew was that, hey, I actually happened to look out the window at exactly 1 hour and saw that we were at mile marker 160. So I know that f of 1, when I plug in a 1, I should get out a 160. But all I have here is this, so I'm going to plug in a 1 into here, and I get 60 times 1 plus c is equal to 160. So that gives me 60 plus c is equal to 160, so that c is equal to 100. And he says, the c is equal to 100. But if he didn't have that point, he could have used another point. And like the easiest one to use, but if you happen to know where you start, if you happen to know that f of 0 is equal to 100, well, that makes your life a little easier. In this case, not all functions are so nice, but they usually are. If you plug in a 0, it almost always makes your life better. So 60 times 0 plus c equals 100, so that c is equal to 100, and we come to the same conclusion. You also could use 2, plug in a 2, get out a 220, use this, and you'll find in every case that c is equal to 100. Now, in general, Victor solved a differential equation, right? He had v, he knew that his velocity was equal to 60. But velocity is f prime. That is an equation that has a derivative of a function. Turns out this one's easy, you just integrate it. That's very simple, right? But nonetheless, he found that the solution to this differential equation is a family of functions. But he doesn't care about the infinite family of functions, right?
Yeah.
He cares about the one particular solution. And what we needed to do, so in general, here we go. In general, you have some differential equation, which involves y prime equals something. Some function involving maybe x, maybe y itself, and involving derivatives of y, etc., maybe other derivatives of y, blah, 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 blah. And what you get is some y of, I guess we're calling it x, right? And there's some constant involved. Maybe it's c times e to the t. Maybe it's like this where, or I'll use t. T is your input. Okay? Or maybe it's something like this. You have 60t plus c. Maybe your c shows up in the denominator where you have t squared minus c, something like that. But in order to find the particular one of your family, what you need is, in this case, one input and one output. So what you do is you say, well, at some specific time, I have some specific output. Another way of thinking about that is you have a point somewhere up here. Here it's at 1, 160, but in general it's going to be at t0, y0. So this is your t0, y0 right there. Right? Yeah. Another way of looking at all of this is to say, Victor looked at this and said, well, I know what my solution's going to look like. It's always going to have a slope of 60 no matter where I am. So he's always going to look like this. It has a slope no matter what. My function is going to have a slope of 60. So if I know where I started, if I know wherever it was that I started, or at some point that I was along the line, if maybe I was here, and I know that I was here, right, at 160, then, or I don't want to use that, then my solution should look like this.
Yeah.
If I know that I started here, then my solution would look like this. The only thing we need to do is say, well, hold up, I actually do have a point. I know that when I plugged in a 1, I got out a 160. And so of this infinite family of solutions, you could zero in on the one that goes through here, and that's the one you're looking for.
Yeah.
Right? Okay, so there's just a bunch of different ways of thinking about this. This is called, so finding the particular solution. What was it saying? So yeah. Finding the particular solution. Which satisfies this is called which satisfies the t0, y0. In other words, the point, right, or whatever, the point, the relationship that y of t0 gives me y0 as an output. This is called the initial condition. And what's confusing is that it's called the initial condition whether it occurs here at 1, or here at 2, or here at 0. It's usually at 0. It's why it's called the initial condition, but not necessarily. They could say the initial condition f of 3 equals 7. That's still called an initial condition. Okay? Okay? You guys got that? So you have some infinite family of solutions. Any point which tells you which one it is called the initial condition. And finding the solution that satisfies it is called, so Finding the particular solution which satisfies the initial condition is called solving the initial value problem. From now on, IVP. So I say we have an IVP. We have an initial value problem. We have some differential equation. This is it. And we know that at 1 we were at 60. Solve the initial value problem means find the particular solution which goes through that point right there. Final, we're almost done. We have one quick one. Everybody with me so far?
Yeah.
Okay. So, very last thing. Solve the IVP y prime equals x. Y, given that y of 0 equals 2. Now, yeah, 0, nice. So that's initial. I could have said y of 3 equals 2, and it would still be an initial value problem. Just because it's 0 doesn't. That's not what makes it initial. It's just annoying. It's almost always initial being 0. Because usually you know what your population was when you started off. Noah knew where he was when we got on the highway, etc. Right? So, okay. So we already know from our earlier work, well, you guys don't know, I just told you, that y of x should be c e to the 1/2 x squared. We verified that when we take the derivative of that, we get x times that.
Yeah.
So now all that we need to do is just find the particular value of c. So what we have here are some family. They're not bell curves. If it were negative, you'd have bell curves, but here you have these. You have some family of these bad boys. It should always be positive unless c is a negative number, in which case it'll do this. Right? Right?
Yeah.
Should look like that. So now we want the particular one so that when I plug in a 0, I get out a 2. We want to know what c makes that one. And so it's very simple. I just plug in a 0 and declare that I will get out a 2 no matter what. So c e to the 1/2 0 squared. So 2 equals c e to the 0. 2 equals c. Therefore, the solution to the initial value problem is y of x equals 2 e to the 1/2 x squared. Now that function should be this one right there. And it should still have this property. And that's what I'm going to check right now. I'm going to check that it has both properties. Plug in a 0, get out a 2. Yeah, that one's good. Now let's do the hard part and check that when I take the derivative of it, y prime, let's see, 2 comes along for the ride. The derivative of e to the stuff is just e to the stuff. Now I gotta multiply by the derivative of the inside stuff, which is 1/2 times derivative of 2 comes down, 2x, 2's cancel. I get 2e to the 1/2 x squared times, all that just works out to plain old x. I'm going to rewrite that as 2x e to the 1/2 x squared. That's my y prime. Now, is that the same thing as x times y? Let's see. X times y is x times y, we claim is that 2e to the 1/2 x squared. That's 2x e to the 1/2 x squared, which is the same thing as y prime. So yes, that is the particular solution to the initial value problem. Nothing really new. We've done all this stuff before. Now we're just bringing in new terminology, and I guess we did do a direction field. That's what that thing was called, or slope field. When I did this thing and said, okay, its slope here should be like this.
Yeah.
And its slope here should be like this. That's new, but we're going to go into detail on that next time, on Thursday. How to make those guys. But everything else, really, we're just putting words to all this stuff that we've already been doing all year.